Okay, good morning. This is Professor David J. De Los Reyes. Okay. My topic for this morning will be, it's now July 24, 2023. My topic for this morning will be a long video format. It's a lecture. This will now be AC circuit lesson number 2. So this will be a topic on AC circuit. Okay, let's proceed. The lesson for this morning will be a long video format. The title of the topic is Alternating Current Circuit Lesson number 2. And the title is Rectangular and Polar Representation of Impedance. Rectangular and polar representation of impedance. The foundation of AC circuit is actually the rectangular and polar representation of impedance. So this will now be an application of our knowledge of the so-called complex numbers. Meaning complex number, it got a real part and the so-called imaginary part. Okay, let's proceed. For case number 1, if the impedance is a pure resistance load, pure resistance, okay, it's a pure resistance load. An example of that one will be lightings. The lightings in our houses are considered pure resistance load. Okay, if we try to bring out the equivalent of pure resistance load as a function of impedance, because we all term the opposition offered to the loop alternating current in AC circuit is actually impedance. For case number 1, which is a pure resistance load, okay, this will be the circuit diagram. This is the resistance load. It comprises of lights. Many lights maybe. How many kilowatts will be, okay? And this is an AC source. So this is just a representation. This is the compressed value of R. Compressed meaning it comprises of many lights. So it is just represented by R. If we try to bring out the vector diagram of the equivalent of this as an impedance, it will just be simply a straight line. Okay, this is R. Because supposed to be, it is always a right triangle. Okay? But for a pure resistance load, this portion is actually 0. This portion is 0. Okay? So if the vertical part is 0, of course the hypotenuse will be 0. Right? So what will remain will just be simply this side here. And that is actually R. It is this. Okay? It got no vertical component. The upward component and the downward component for a pure resistance load, meaning X of L is 0, X of C is 0. Pure resistance load. Okay? The resulting triangle will just be simply a straight line because it got no vertical component. Nothing is this one. So the hypotenuse is 0, so what will come out will just be simply a horizontal line. That's the vector representation. Okay, I try to remember that one because for as long as we are leaving the vector representation for a pure resistance load will just be simply a pure horizontal line. Okay? That is represented by R. Okay? Okay, let's try to bring out the rectangular form. Why the rectangular form is important? It is important because in the calculation of the current, because for sure there will be a circulating current here. Okay? To compute for the circulating current, we must have to compute for the impedance A. Okay? And for a pure resistive load, in terms of rectangular form, meaning rectangular, it got the real part and the imaginary part. The impedance under case number 1 will be R plus J0. The imaginary part is 0. It got no upward part, it got no downward part, it is just horizontal line. So Z is actually R plus J0. The unit is ohms. Okay? How about the polar form? The polar form will be in terms of its magnitude and angle of inclination or direction. Okay? So this here should be the absolute value of R. Absolute value, meaning just the magnitude. This sign here is angle. Okay, we try to read this absolute value of the impedance for a pure resistive load will be the absolute value of R, angle 0 degree. And the unit is still ohms. Okay, that's the representation. So try to remember that one. For a pure resistive load, the impedance in terms of polar form, the impedance is actually the absolute value of R, just the magnitude, angle 0 degree ohms. Okay, that's this. That's how we read this one. The impedance for a pure resistive load is just the absolute value of the resistance, absolute value, just the magnitude, angle 0 degree. Okay? Let's go with case number 2. So for case number 1, it is just an easy one. We got no triangle here, it's just a horizontal line. Okay? So the rectangular is R plus J0. It got no vertical part which is going upward or downward. It's just 0, J0. Okay? And the polar form is the absolute value of R, angle 0 degree. The angle here, it is horizontal, right? So theta is actually equal to 0 degree. Okay, for case number 2. If the load is inductive, that's the time we are saying that the load got motor loads, okay, like water pumps, maybe air conditioners, right? But if we say inductive load, there should be a resistance in series with it. So for inductive load, this is actually a combination of a lighting load and motor loads. That's why it is termed to as inductive load. Inductive because there are motor loads. But there are lightings also. So if we try to bring out the diagram, it will be this. AC source in series with the lights, in series with the motor load. Okay? And the vector representation of the impedance will be this. There is now the so-called the right triangle. So this is now an application already of trigonometry. What we learn for the sine cosine function, we apply it here. Okay, so for case number 2, there is a right triangle. This is R, this is X of L, and the hypotenuse is actually the impedance. Okay, the angle between R and Z is theta with the subscript L, meaning for motor loads. Right? If we try to bring out the equation for the rectangular form, okay, it will be Z equal to R plus J X of L ohms. You notice it? This is an X of L. And here, it is 0. Pure resistive load, right? But for inductive load, there is an X of L. So the rectangular form for case number 2 will be Z will be equal to R plus J X of L. Okay? And which the value of X of L is the product 2 pi times the frequency times the inductance, where small letter f is the frequency in hertz. We discussed that on the first lesson. And L is actually the inductance. The property of a motor that got coils is actually inductance, and the unit of that is actually in henries. Okay? So this is in henries. This is in hertz. So meaning to say, to compute for the inductive reactance, you just multiply 2 pi times the frequency times the inductance. Okay? That's the rectangular form. For the polar form, the total impedance will be the absolute value of the impedance angle theta L. Okay? There are three formulas on how to compute for the magnitude of the impedance under case number 2. Formula number 1 is the absolute value of the impedance is actually R over cosine of theta L, and the next one will be X of L over sine of theta L, and the third one is actually the square root of the resistance plus the square of the inductance, then take the square root. So in the computation of the absolute value of Z under case number 2, you could take one of these solutions. You either use R over cosine or X of L over sine, or just simply the Pythagorean problem or Pythagorean formula. Why absolute value of Z is R over cosine of theta L? Okay, that's trigonometry. If we try to take the cosine of theta L, cosine of this will be adjacent over hypotenuse. So it will be R over Z. So if we try to compute for the absolute value of Z, it will be R over cosine of theta L. It is this. Okay? For the sine function, it's the same. Sine of theta L, sine of this angle will be the opposite over hypotenuse. So this will be X of L over Z. So this is X of L, and this is sine of theta L now. This is Z, the absolute value of Z. Okay? It should be X of L over sine of theta L. It is the second equation. And for the third one, if you do not want to use the cosine function and the sine function, okay, use the Pythagoras theorem or Pythagorean theorem, right? It will be the square of R plus the square of X of L, then take the square of, that is Z, the absolute value of Z. Okay, that's it. That's the third formula. So it's up to you what equation you will be using. So you will be needing a scientific calculator with the sine cosine function, because in the computation of the magnitude, if you want to use the cosine, use the cosine. If you want to use the sine, use the sine. If you want to use the Pythagorean theorem, okay, square this one plus the square of this, then take the square root. There is a square root over here. So actually you can present three solutions. Okay, that's case number 2. For case number 3, if the load is capacitive, meaning the load is capacitive, okay, the load is capacitive, it will be capacitors. Okay? But this capacitor sometimes, for it, there is actually a load in which it is a motor that if we try to overexcite it, it will act like a capacitor. That's the one being, okay, proposed by Elon Musk, right? To, what you call this, to minimize your current consumption. That is actually a capacitor, which will be connected in series with the main line, right? Because the inductive load, it will be contradicted by the, what you call this, capacitive load. So what will come out will just be simply a pure resistance load. So if your total Z is simply R, actually your current consumption is less. Okay? So for case number 3, if the load is capacitive, okay, for the meantime, let's assume that the load is capacitor. The circuit diagram will be this. AC source. If we see capacitive load, there is a lighting load in series with it. So there are lights and there are capacitors. Or capacitors, or maybe synchronous motors which are overexcited to act like capacitors. Right? So the vector representation for the impedance of this, it will be a right triangle that goes downward. Right? This is R. This is X of C going down. and this is the impedance. For the inductive load, the imaginary part is actually upward. This is downward. Okay? So for the rectangular form, R will be minus J x of C. This is minus. Okay? Because it's going down over here. Right? Ohms. Where the value of x of C will be 1 over 2 pi f C. Okay? It's the reciprocal of this. It should be where the small letter f is the frequency in hertz and capital letter C is the capacitance of the capacitor in microfarad. This is a symbol for microfarad. This is 10 to the negative 6. Okay? So if you try to read this one, we read this one as microfarad. That's the unit of capacitors. Okay? For the polar form, the impedance will be the absolute value of Z, the absolute value of the hypotenuse. Okay? Angle minus theta C. This is minus. Okay? This is minus. On the inductive load, this is plus. Right? This is minus because this is downward. This is plus because this is upward. This is plus theta L actually. This is plus theta L. This is minus theta C. It's down, right? So in the computation also of the absolute value of the impedance, it's the same as here. It will be R over cosine of theta C or x of C over the sine of this, sine of theta C, or the last one, it will be the square root of R square plus x of C quantity square, then take the square root. Okay, those are the three possible cases of impedance under AC circuit. It could be a pure resistance load for case number 1. Case number 2 will be an inductive load. It's a combination of lightings and motor loads. And case number 3, it's a capacitive load. It's a combination of lighting load plus some capacitors or synchronous motors which are overexcited, okay, to act like capacitors. Okay? So, the three possible formulas for the three cases, what is important here is the polar form. Case number 1, impedance will be the absolute value of R angle theta 0 ohms. Case number 2, it will be the absolute value of Z angle theta L ohms. This should be plus. And for case number 3, it should be the absolute value of Z angle minus theta C ohms. Okay, so that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys, okay? If you want to subscribe to my channel is at youtube.com/@ProfDavidJ. If you want to share it, please click share. Okay, try to watch my videos. You will learn something from it. Okay, good morning from Los Angeles. This is Professor David J.